Hi. So today we're looking at alternating current. This is basically the electricity that comes into your home through the mains, not like through the door. And we're going to describe what it is. So by the end of the lesson, we'll describe what alternating current is and how it was sent around the national grid and why it's sent around the national grid. It's a lot of information today, not so many mathematical questions, if that helps. But let's start us off. Let's review some of the things we've done in the past. So name 5 components in a circuit that would have some kind of resistance. What's the rule for current in this series circuit? What's the rule for potential difference in a series circuit? What's the rule for current in a parallel circuit? And what is the rule for current potential difference in a parallel circuit? Simple rules. Make sure you don't get them mixed up. Pause the video and answer those questions before we go any further. Have you done them? Splendid. 5 components in a series circuit. In a circuit that would have resistance, a cell that will have resistance, a resistor that will have resistance, a variable resistor, also resistance. You could do a thermistor, or you could have done an LDR. Those are 2 arrows, I've gone in the wrong place. You could have also done something like a diode. It has resistance in one way. Yeah, they're the main ones. A voltmeter as well has resistance. If you said ammeter, no, it doesn't. What's the rule for current in a series circuit? It's the same everywhere. In a series circuit, the current is the same everywhere. And what's the rule for potential difference in a series circuit? It's shared between. It is shared between the components. If you get 6 volts from the battery and there are 2 components, they'll each get 3 volts each. What is the rule for current in a parallel circuit? Current splits at a junction. So if the circuit has 2 routes, current half might go the one way and half might go the other way. It depends what's in the different branches, but the current splits at a junction and then rejoins. So whatever splits apart must come back together later. And what's the rule for potential difference in a parallel circuit? Potential in a parallel circuit is same PD as battery across each branch. Very simple, but really, really fundamental. And if you know those things, the rest of electricity becomes really, really easy to do, especially calculations. So if you know those things, do it. If you don't know those things, spend some time rereading them, going over them again. They are the fundamentals and so important when we're learning about electricity. Okay, so direct current and alternating current. Everything we've done so far has been about direct current. And, sorry, I'm at my door. Give me a second. So with a direct current, you have a battery or a cell, and what happens is the current flows in one direction. Now, I know there's that weird thing where we talk about current goes one way, but actually the electrons go the other way. But if we're just talking about the current in a circuit goes from positive to negative, and it goes in one direction. It's always going from positive to negative. But alternating current goes both ways. But it doesn't go both ways as in there's a stream of electrons going one way and then another going the other way. What happens is the same electrons shimmy along like this. And I suppose the easiest analogy I could think of is like, with direct current, it's like when you're trying to, say, move something from one place to the other. And what you do is you walk, say you're unloading a truck and you're moving things from your house, from the truck, into your house. And a direct current would be the equivalent of you go into the truck, you pick up your thing, you walk to the house, go into the door, you drop it down, and you come back to the truck and you pick another piece up and you go through to the door and put it out. And if there's more people and they all work together in that same way, that would be like a direct current. So you pick one thing up, another person picks another thing up, a third person picks a third thing up, and you walk into the house and you drop it down and you come back and you all take a new piece at a time. That's the direct current model. So everyone's going around, but they're all doing their own thing. Alternating current would be like if you empty in your truck and there's your house there, but you have like a row of people. And what happens is one person takes the thing off the truck and they pass it to the next person. And then the next person takes that thing and passes it to the next person along, and the next person, and they're doing this whole thing. So what's happening is they're going that way to collect, and then that way to pass off, and collect and pass off. So alternating current is when the electrons go both ways, but the whole packages, say if you're unloading the truck, the stuff still gets into your house, but the people who are unloading it, they don't move, they just kind of stand in a row and swing one way and put it back, and the other way, put it back. Appear to be dancing at the moment. So there is another little animation on the FET thing. So here we have an example of the alternating current. They go this way, they go that way. They swing left, they swing right. They're still transferring their energy. They take a bit of energy, they pass it to the next person. They take their piece of energy, they pass it to the next person. So the alternating current, the electrons move forwards and backwards. They don't really go anywhere. That electron up here isn't really ever going to make it here, but he will pass his energy along to the next electron, who will pass it to the next electron, who passes it to the next electron, and the next electron, and the next electron, and so on, until the energy gets round. And if they keep passing the parcels, simple. Just done a lot of talking there. It's worth noting that if you look at that bulb, what's happening? It's flashing on and off. So if this was how the electricity gets into our house, if you turn your light bulb on and the AC goes on, why don't the bulbs flash? They do. But the problem is they go so fast, and it's not really a problem. The thing is they go so fast that your eyes can't even detect it. And actually you can. Sometimes if you film, say, the lights with certain cameras and you get the right shutter speed, you can see them flickering, you can see them flashing. Sometimes you can get it so it appears dark all the time. So this works quite fast. In fact, let's look at that bit again. So I've done that already. That's the FET thing. And then there's a nice good fact. If there's anything to do, I'm going to ask you to take a note. In a second, I'm going to ask you to pause this, draw that, and take a note. I'll explain what that means in just a second. So pause, draw that diagram, take those notes, go. You've done? Check. All right, I'm just going to load this animation, and then we're going to look at what it means. So let's go back to this for a second whilst that unloads. So we have two different types of current. We have alternating current and direct current. And if I were to draw a direct current graph, it's really simple. Here it is. Straight line. Nice, straight, simple line. Current's always the same, go in a straight line. An alternating current, I told you, this goes one way, then it goes the other way. It goes one way, the other way. We represent it on a graph like this. If we're at school, we might plug an alternating current into an oscilloscope, one of those big boxes that has the lines that go across, and we might see that alternating current. And I told you it happens really fast, and it happens at something called 50 hertz, which is 50 up and downs per second, 50 cycles per second. Let's look at the animation of what I mean by 50 hertz. So this is a simple wave on a string. Turn the damping off. So we'll do waves on another topic, but here's a good example. So this is a wave traveling up and down like this. It's moving up and down, but it's traveling left and right, and that's my wave. If I increase the frequency, look what happens. It's going up and down more cycles. This one can only go at up to 3 hertz. The light, the electricity in your house comes in at 50 hertz, so 50 of those up and downs every second. So it's really, really fast. So the frequency of your mains electricity is 50 hertz or 50 cycles per second. If you want to do the equation, to work out how fast that is. If you do 1 over the frequency, that tells you how long each cycle is. And if you do 1 over the frequency, 1 divided by 50 is 0.02. So it goes up and down, back to the middle. That's one cycle in 0.02 seconds. So that's incredibly fast, 50 hertz, very fast changing. And that leads us on to how electricity is transmitted. And there's quite a big history around this. Two of these very famous inventors, Thomas Edison and Nikola Tesla. I'm going to very super truncate this story, but basically Edison is an incredibly famous inventor, as is Tesla. Edison is an incredibly good businessman, and Tesla isn't. Tesla, they basically hate each other. Edison had the copyright to some of Tesla's inventions. There's a terrible animosity between the two. But Thomas Edison has created this thing. He's not created direct current, but he's marketing and selling direct current, trying to get like all the streetlights and the houses in America to use direct current. Nikola Tesla has kind of sold or given one of his inventions to a businessman called Westinghouse, and he's trying to persuade their country to use AC, alternating current electricity. AC is better, and that's what we use nowadays. But Edison was a ruthless businessman, and so Edison and some of the people he worked with, what they would do is they'd go around different towns and collect dogs and cats and use AC current to electrocute and kill the dogs and cats in front of people, trying to tell people how dangerous this electricity was. Tesla and Westinghouse weren't quite as sick and twisted as Edison was, so they didn't do those sort of things. In fact, as time went on, Thomas Edison and his team, well, I don't think it was him directly, got more and more desperate to kind of sell their things. So they started killing bigger animals, horses. They ended up killing an elephant. They electrocuted an elephant to death with the AC. And then that's the reason that in America they have the electric chair, because of Thomas Edison and his other people persuading the American government that the electric chair would be a more humane way to kill it. The first time they used the electric chair, it was such a disaster. The people witnessing it said it would have been kinder if a person had been killed with an axe. So a little fun, cheery history for you to read between the two. AC won. DC didn't win. AC won. And there's a reason for that. And the reason for that is how you can send it out. So, oh, my head's in the way. Oh no. So with AC, what you can do is you can do something, you can step it up and you can step it down. So because of, it's tricky without explaining how it's generated, but basically if you put AC through a transformer, without cheating the laws of physics, if you increase the voltage but decrease the current, you keep the same power, so you've not like made energy, but you can change your electricity so it's more voltage but less current. Or if you step it down, you can go the other way. You can decrease the voltage and increase the current without kind of losing anything. And it's really important because if we think about resistance from a couple of lessons ago, current, what is current? It's those electrons flowing along. And what happens to electrons in the wire? What do? They collide with the atoms, correct? So they collide with the atoms. What happens when they collide with the atoms? Those atoms vibrate more. And what happens? They get hot. As they get hot, they vibrate even more. And what happens to the resistance of that wire? It goes up. And then in a strange kind of feedback loop thing happens is then the wire gets hotter and then more resistance and hotter and more resistance. So actually, if you try to send electricity with a high current, the wire will get so hot that it can't go very far and it just stops. And that's why Edison's version didn't work, because he would have had to have a power station like on every block, which would have been crazy. Whereas with Tesla and AC, if you transform it by moving the voltage really high and the current really low, you can send it for massive distances across the entire country and you don't lose that much energy. And then when you get back to people's houses or businesses, you do the opposite. You step down, you decrease the voltage, increase the current, and then you just send it to people's houses. loads of information there. I would note maybe you want to write that down. So for a step up, you increase the voltage and reduce the current. My head's in the way, sorry. For a step down, you decrease the voltage and increase the current. So we start here. Power station might produce 25,000 volts. You put it into a step-up transformer, and the voltage goes up, and the current goes down. And that means when you put it in something like a power line, when you have incredibly high voltages, but relatively low currents, it can travel along the wire without the wire getting too hot and melting and losing energy from having too much resistance. The step-down transformer does, depending on where it's going, steps down the incredibly high voltage, decreases the voltage, increases the current. If you're going to, say, a big building, a factory, a hospital, they might keep quite a high voltage because they might use big machines. And so you might have like 30,000. Or it'll go on to our homes. Maybe there'd be more step-down transformers going down to just 230 volts inside our house. Really clever way. So transformers can change the voltage and the current. They have to change together. One goes up, the other one has to go down to keep everything balanced. I think it's a good idea for you just to pause, write down those notes, and then I'm going to have another explain about transformers. Okay, good. So remember, transformers can increase the voltage, decrease the current, decrease the voltage, increase the current. Now, in your house, you've probably got lots of transformers already. You maybe just didn't know. 230 volts coming through the mains is quite a lot. That's enough to power your washing machine and tumble dryer. If your oven's electric, it's enough. But there are some things in your house that if you put those 230 volts and 13 amps, it would actually be really bad. It would damage them. So you've probably got lots of transformers in your house. My laptop, which I'm recording this on, has a transformer. So you've got the wire that's plugged in, and there's this block here. If any of your devices have a block like this, that generally means it's a transformer. Laptops are a great example. Xboxes and PlayStations, games consoles often have a transformer. Sometimes the transformers are quite clever, and instead of having an extra block like this, it's inside the plug. So the plugs might be a bit bigger. Normally phone chargers have a transformer inside the plug because they're another way of having a transformer. So if you've got a device in your house that doesn't want to use all 230 volts from the mains, it might have its own transformer inside. These transformers, you've seen them around actually. If you walk down the street and every now and then you might see like a small building or maybe just a green box that says danger of death, stay away, keep away or something. That's a transformer. That's your transformer near your house. The mains electricity in London is coming out of the ground rather than across the wires above us. And those would be the transformers where it's then stepped down and sent around to your houses. So why would you use a transformer? So why would you use alternating current? It's because you can transform. And why do you transform? You want to transform because if you use a lower current, that means you get less heating. If you have less heating, that means the resistance won't go up as much. If the resistance doesn't go up as much, that means you don't lose as much energy, so you can transmit your electricity with almost no energy loss. Okay, so I have done a lot of talking, and I apologize, but it's the way to do it, I think, for this lesson. So here we have some questions. All you have to do is fill in the missing words. The National Grid takes from power stations to businesses and homes at extremely large voltages. It does this to limit the loss by heat from the wires. The bigger the electric, the more the wire is lost, the more heat is lost. To make the voltages bigger, a step up used. To make the voltages step down, transformers are used. So simple. And the last question. Will a transformer work with direct current or alternating current? What is meant by a step-down transformer? What is meant by a step-up transformer? Write down one appliance you would expect to find a step-down transformer, and then write another appliance place you might expect to find a step-up transformer. Okay, lots of information, but done really well. Love you. Bye.